Hello, everybody. So what we're going to be looking at today is section 4.3 in your book, which is partial derivatives. Um, so this actually is a short topic for once. I'm not lying this time, I'm pretty sure. Um, and this is what we're going to do. We're going to learn how to calculate partial derivatives. Part of that, of course, is going to be writing down what the definition of a partial derivative is. And we're going to look at some higher order partial derivatives. Anyway, this is a good topic. I liked it when I had this class, and I think you'll like it too. It's not so bad. All right, so let's go ahead and write down our definition of a partial derivative. The idea is very simple. So consider a function. Oops, got it right. Need a pen. Consider a function of two variables. Doesn't have to be two, but we're going to start with a function of two variables. So consider a function of x and y. How about f of xy, right? Now, when you take a derivative, you always take a derivative with respect to a variable, right? In Calc 1, you learned derivatives. You learned how to compute derivatives. Yeah, you learned how to calculate, or you've learned how to compute derivatives with respect to a certain variable. So of a function with respect to a certain variable. Of course, now we have multiple variables in a single function. So we have two variables or more. So if we have two or more variables in a function, what do we do? What to do? Well, it's actually pretty simple. What we're going to do is you're only going to take the derivative with respect to one variable at a time. So if you've got two variables, well, there's one derivative for the x variable and one derivative for the y variable. And we'll call those partial derivatives because, well, you're not finding like the entire derivative of the function, whatever that means. Okay. Basically, all we're going to do, we're just going to take derivatives. Keep doing that. We're just going to keep doing that. Taking the derivative with respect to a single variable. Okay, and we call these partial derivatives. And so here's our definition of a partial derivative. Definition. So let f of xy be a function of two variables. I'm just going to say a function because you can see the two variables. So we got two things here. We got the partial derivative with respect to x is, so we write it this way. So in calculus 1, you wrote like derivatives like this, right? Like df dx. That was something that made sense, right? And we're going to use kind of the same notation here, but we actually use like a delta symbol. So we actually use, instead of a d, we use this symbol, a delta. So we'll have delta f, delta x, but we just call that, I mean, you generally people still read that as df dx. It's just not a regular d. Okay. You can write it that way, or you can write it f with a subscript x. So the subscript indicates the derivative. In any case, the way you're actually going to calculate it, actually not the way you calculate it, but the definition of it is the limit, that's a terrible m, the limit as h goes to 0 of f of x plus h y minus f of x y over h. Okay, and so notice that from here to here, the only thing that changes is this is x plus h and this is x. So normally, if you wanted to make this the definition of the derivative that you get in calculus 1, you would just delete these y's. Oops, not the. You would delete that y and delete that y. And this is the definition of the derivative that you have from calculus 1 with respect to x. And we've got an extra variable y, but we're not taking the derivative with respect to y now. So we just kind of just leave the y in there. Okay. And then if you're going to do the derivative with respect to y, the partial derivative with respect to y, then what you would do is you would just do the exact same thing. So the partial derivative with respect to y, x, y plus h, x comma y. That's wrong variable here. Okay, there you go. So the point is that each of these just looks like the definition of the derivative from calculus 1. Let me just kind of fix a little bit. Okay, there we go. So those are your partial derivatives with respect to x and with respect to y, and they're just the definition of the derivative from calculus 1, but we're keeping this other variable just along for the ride. Okay, so let's see here. Just make a note of a couple things. The symbol is not a D. Okay. And generally you would read like df dx. You wouldn't actually read it df dx like I just said. You would say the partial of f with respect to x. Okay, so the partial of f with respect to x. So yeah, so the d's not, or the round d is not a d. All right, so how would you do that? So maybe we'll do kind of one with a, I'm going to do one derivative with the definition, and that's all we're going to do with the definition. They really do work exactly the same as calculus 1. So I'm just going to do this one time. So use the definition. You should not do this in the homework, by the way. Unless you just want to understand better. So use the definition. You should not do the homework. To compute partial of f with respect to x of, and I need a function of two variables. I'm gonna make it not too hard. I'm gonna go 5x squared plus 4xy. Okay, so there's a function with two variables. Actually, let's go y squared as well. Okay, so there's a function of two variables. Now, we're going to use this definition. So by definition, partial of f with respect to x, or you could call it f subscript x, is the limit as h goes to 0, f of x plus h comma y minus f of x y over h. Now, since I used kind of like not the shortest function in the world, I'm going to need some room here. But let's see here. So we're going to plug, first of all, f of x plus hy. So we're going to plug in the x plus h in for all the x's. For y, we just plug in y, which means all the y's are going to stay the same as they are. So we're going to end up with 5x plus h squared plus 4x plus h y plus y squared, right? So I've just replaced the x's with x plus h. And then minus f of xy. Well, f of xy is exactly what the function is. So we're just rewriting the function there. Okay, over h. Now, you would have to work out all of those things that are multiplied here in the numerator. It's not so bad. You just have to FOIL the x plus h, really. So we're going to end up with 5 x squared plus 2xh plus h squared. Plus, here you can just multiply, you can multiply this all out. Like if you multiply the 4 and the x and the y, you get 4xy. If you multiply the 4, the h, and the y, you get 4hy. Then you've got your y squared. And then here, I'm just going to, I want to maybe just distribute this minus through here so I can get rid of these parentheses. So minus 5x squared minus 4xy minus y squared over h. Let's just finish multiplying stuff out before we cancel stuff here. So let's multiply this 5 all the way through here. So we get 5x squared plus 10xh plus 5h squared plus 4xy plus 4hy plus y squared minus 5x squared minus 4xy minus y squared. Yay! Over h. Now, what we want to do now is just cancel everything that might cancel, which is going to be probably a lot of stuff. So, for example, there's a 5x squared here and a negative 5x squared over here. Also, there is a plus y squared and a minus y squared. And also there is a 4xy and a negative 4xy. What we're left with is what? Let's find out. So we're left with a 10xh, a 5h squared, and a 4hy over h. Everything has an h in it, so we can factor out an 8. And we'll have 10x plus 5h plus 4h. Nope, we're factoring out the h. So just 4y over h. Let me stop and look at this and make sure I did it right. Okay, I think I did. We can cancel those h's, right? So now we've got the limit of what? We have the limit as h goes to 0 of simply 10x plus 5h plus 4y. So in order to evaluate that limit, we can just plug in h equals 0 now because there's no divide by 0, like 0 over 0 indeterminate form shenanigans going on. So we can just plug in h equals 0. We get 10x plus 5 times 0 plus 4y, or simply 10x plus 4y. Okay, so that's our derivative. So let's look at this. Now, so our function was what? Let's see. So f of xy was somewhere 5x squared plus, why can't I remember things? 4xy minus 4xy? No. Plus 4xy plus y squared. Okay. Now, the thing here is that if you look at what's going on, we can see what happened. The derivative of this with respect to x is just 10x, right? So that makes sense. And here, the derivative of y squared with respect to x is actually 0. There's no x's. Okay? So that makes kind of sense. And the derivative of 4xy here turned out to be 4y. Now, what's going on to make that happen? If you want to skip the definition, you can get the same answer far more quickly by understanding that when you do a partial derivative with respect to a variable, you're basically just treating the other variable like it was a constant. Okay, let me write that. So to take or to compute the partial with respect to x, you treat any other variables like y and z as if they were constant, and just take a regular derivative with respect to x. Like you would in calculus 1. Okay, that's the punchline here. That's how you do these. Now, the hardest part of doing that is going to be just to, you've been trained to take derivatives by like recognizing when there were variables around, so you knew when to do product rule or quotient rule or chain rule or anything like that. And you kind of have to untrain yourself of that a little bit because now only one of the variables is a real variable and the other variables look like variables, but you're treating them like they're constants, right? So like, for example, um, when computing partial with respect to x, right? If you do the partial with respect to x of a function of x, like x to the fifth, of course, you're just going to do the derivative like normal, right? Power rule. So very simple. Now, if you had the partial with respect to x of like 17x to the fifth, right? Then that 17, which is just a constant, you would just keep the 17, and then you would take the derivative 5x to the fourth, right? Isn't that what you would do? So now if you take that same thing and you put like a y there, like y, let's do say y to the seventh, x to the fifth. Well, we're just treating the y like it's a constant. So y to the seventh is just a constant. So just like you just kept the 17 here, you're just going to keep the y to the seventh. And then the derivative of the x to the fifth would be 5x to the fourth. Okay, so we're treating that y to the seventh just as if it was a constant. Oops. Okay, and that's how these go. And so let's see, what else can we do? Maybe something like this, slightly more complicated. What if you have a partial with respect to x of like sine x squared y squared, right? So this is more like a regular example, so I'll label it as an example. Like, what would you do here? Well, this would require the chain rule, right? Needs a chain rule. So what you would do to take that partial is you take the derivative of the outside function, right? So you start with the sine. The derivative of the sine function, of course, is cosine x squared y squared. And then you have to multiply by the derivative of what's inside, which is partial with respect to x of x squared y squared. And when you do that partial with respect to x of x squared y squared. Again, you got to remember that you're regarding the y squared as if it was a constant. So you have to remember that, treat as constant. And then you would end up with cosine x squared y squared. And the partial with respect to x of x squared y squared, you just take the partial of the x squared part, which is 2x. And the y squared is just carried along for the ride, right? Treating it like it's a constant. So there it is. Okay. So mostly that's not hard to understand, but it does take a little bit of, effort to remember. Now let's do a few that are just y's, right? A couple more examples. Like let's try find dg, not dg, partial of g with respect to y of some function of g of xy. What's g of xy? Let me think. Let's go natural log x squared y over y squared plus x squared. Will I regret this? Probably. But, this is how we practice. So we need the derivative of this with respect to x. So we're performing, so partial of g with respect to y is the partial with respect to y of this thing. Now, you know how to do this. The derivative of the natural log function is 1 over whatever it is, right? So the derivative of the natural log of x is 1 over x, for example. So we take this derivative here. It's going to be 1 over x squared y over y squared plus x squared. There is a much easier way to do this, by the way, but we are taking the long way, the scenic route. So it's 1 over that, and then times the partial with respect to y of this thing, x squared y over y squared plus x squared. So in order to do this derivative, we need the quotient rule because, well, we've got y in the numerator, we've got y in the denominator. So, even though we're treating the x's as constants, the top's not a constant because of the y, and the bottom's not a constant because of the y squared. So this does need a quotient rule, the way I've got it written anyway. So what do we got? We have, first of all, 1 over this thing is going to be, we can write this as the reciprocal of this. So y squared plus x squared over x squared y times, and this derivative we're going to need a quotient rule for. So it's just the regular quotient rule. So like normally, like the quotient rule, right? Like f over g prime is f prime g minus f g prime over g squared, right? So for this problem, the f is the numerator, right? So like dy, x squared y, that's f prime. Then the g, x squared plus y squared minus f, which is x squared y. And then d dy. I keep saying d dy, but you know what I mean. X squared plus y squared over g squared, which is going to be x squared plus y squared squared. Okay, so we just have two smaller partials to take, right? We got to take this partial now, and then we got to take this partial now. So we're just applying the regular old quotient rule exactly as you learned it before. So x squared plus y squared. I'm slowly putting the x's and y's in order there in various places in the problem. And then we got these two smaller derivatives to worry about. So the derivative here, partial with respect to y of x squared y, well, we're taking the derivative with respect to y. So the derivative of y with respect to y is 1, and the x squared is just along for the ride. So this derivative is just x squared. And then you have x squared plus y squared minus x squared y. And then here you have the partial with respect to y of x squared plus y squared. So the partial with respect to y of x squared is 0, because remember, we are treating the x squared as if it was a constant because our partial is with respect to y. So the derivative of a constant is just 0. So the derivative with respect to y of x squared is 0. Derivative with respect to y of y squared is going to be 2y. And then the bottom is what it is. Okay, so what do we have? We have x squared plus y squared over x squared y times, and there's not a lot to do here, just kind of simplify it, multiply it out, I guess. We can just multiply this out. We'll get x to the fourth plus x squared y squared minus x squared y times 2y. So when we multiply these together, we're going to get that 2. So we're going to have minus 2 x squared y squared, right? Because 2y times this is going to give you 2x squared y squared. I think so. And the bottom is x squared plus y squared squared. We can keep going here. Let me just do the easiest canceling first. So like these actually can combine, right? So let's do that before I deal with anything else that you may see here. So what do we got? We have x to the fourth, and then x squared y squared minus 2x squared y squared is going to be minus x squared y squared, and then over x squared plus y squared squared. Now at this point, what I see is that I can cancel some stuff. Specifically, I see that there's an x squared plus y squared here and an x squared plus y squared squared here. So I can cancel that with one of these, which will leave 1 in the denominator. So we end up with x to the fourth minus x squared y squared over x squared y, x squared plus y squared. Okay. And I'll just stop there and I'll say that that is what the partial of g with respect to y is. Maybe you could do more simplifying. Actually, definitely you could. Let me do a little bit more, actually, slightly more. What I want to do here is I just noticed that x to the fourth, x squared, we can cancel 2 x's off of everything, I think, right? So we can cancel that x squared and take out that x squared, and then this will turn into a 2. So we'll end up with x squared minus y squared over, and then we may as well just distribute this y through here now. X squared y plus y to the 3. So something like that. Now you don't need to simplify it so much. I just was, because on these problems, there's a lot of simplifying you can do. One thing I will say is, back at the beginning, I said I'm not doing this in the smart way. I want to just mention why that was not the smart way. If you were really dealing with this function in a problem, right? So if you actually add this in a problem, you should use the log rules to simplify it before you start. Before you start doing any kind of derivatives. Right, so specifically, right, like if you got the natural, that's not natural. If you have like the natural log of like a over b, right? Natural log of a over b is ln a minus ln b, right? And ln AB is natural log A plus natural log B. And if you had natural log A to the B, that's B natural log A. And so those kind of rules, um, help you simplify before you start. So this one right here, right? You would have gone, before you do anything, it's the natural log of x squared y minus natural log of y squared plus x squared. And then this one, even if you want to, could be ln x squared plus ln y minus ln x squared plus y squared. And even that 2 there can come down in front using this third rule. So you have 2 ln x plus ln y minus ln x squared plus y squared. Now, why would you want to do that before you start? The reason you'd want to do that before you start is because if you do this derivative with respect to y now, so partial of g with respect to y would be the partial with respect to y of this thing, which I'll copy paste, would be partial derivative here. And this time you get to avoid all of that quotient rule nonsense, right? So when you do the derivatives here, the derivative of 2 ln x with respect to y is 0 because there's no y's. The derivative with respect to y of ln y is going to be 1 over y. And the derivative of ln x squared plus y squared is going to be 1 over x squared plus y squared times the derivative of what's inside. So what's the derivative of x squared plus y squared with respect to y? It's simply 2y. So overall, you end up with 1 over y minus 2y over x squared plus y squared. Now that doesn't look like the answer that I got, up here, but if you got a common denominator so you could add these together, the common denominator would be y times x squared plus y squared. And here, this is y times x squared plus y squared. And so presumably, if you actually did get a common denominator and add these together, it should just be this, the same thing that we calculated before. But obviously, one line, 2 lines for the answer was much faster than however many lines I took here. 1, 2, 3, 4, 5, 6, 7. So, keep that kind of thing in mind, that, you can make your life easier by using rules like the log rules and stuff, right? Kind of, getting back in the swing of doing a bunch of derivatives is really what we're doing here. Okay. So let me see if I can come up with something here. Yeah. Let's just do one more of these, kind of just in case we're missing anything. Oh yeah, okay, let's do this. So find partial of f with respect to x and partial of f with respect to y. A lot of times they make you do both. Of f of xy equals tan x cubed minus 3x squared y squared plus 2y to the fourth. Okay, so let's try this. So we'll start with partial of f with respect to x. That'd be partial with respect to x of this thing. Duplicate it. Oh yeah, I forgot that you can't see it when I'm doing certain things. Like when I'm copy pasting something, you can't see it until I do it. Okay, so we need the partial with respect to x here. So this is a chain rule. So chain rule. So you start by taking the derivative of the outside function. You have to remember what is the derivative of tangent. Derivative of the tangent function is secant squared. Everything inside stays the same. And then you have to multiply by the derivative with respect to x of what's inside. So the x cubed minus 3x squared y squared plus 2y to the fourth. Let me just circle that again, duplicate it. I'm just rewriting it down here. So now you just have to do this last derivative and we'll be done. So we got secant squared x cubed minus 3x squared y squared plus 2y to the fourth times the derivative of the bit that's in yellow. So partial with respect to x of x cubed, 3x squared. Partial with respect to x of negative 3x squared y squared. Remember, you're just treating the y squared as a constant. So you're only really paying attention to the x squared there. The derivative of x squared is simply 2x. So you have 2x combined with this 3 would give you 6x. The y squared is along for the ride. Last one, the derivative with respect to x of 2y to the fourth. 0. There's no x's, right? So there you go. That's your derivative. I'm not going to rewrite it just to stop writing that 0. So it's your partial with respect to x. Now, if you're going to do partial with respect to y, you're going to reproduce a lot of that work. Partial with respect to y. Let's change this. Partial with respect to y. Partial with respect to y. It's going to be mostly the same idea, right? So secant squared again, x cubed minus 3x squared y to the 2 plus 2y to the fourth times the derivative of what's inside, but this time it's a y derivative of x cubed minus 3x squared y squared plus 2y to the fourth. So let me just write this here. Okay, caught up. Okay, last derivative. So we're taking the derivative with respect to y this time. So make sure you know that. The derivative of the x cubed, there's no y's, so it's going to be 0. Derivative of a constant is 0. Then you have the derivative of 3x squared y squared. This time, the negative 3x squared is all considered a constant. And then the derivative of y squared is going to be 2y. And finally, the derivative of 2y to the fourth, power rule, we're going to take the 4 down in front, 8y to the 3. So we end up with secant squared, x cubed minus 3x squared y squared plus 2y to the fourth times negative 6x squared y plus 8y to the 3. And that is, you can write it this way. I'll write it this way just because we haven't done that very much. Okay. So, comparing those two derivatives, they both have, like, this secant part is the same on both of them, but then the derivative of the inside is what is different, depending on whether we were doing a partial with respect to x or a partial with respect to y. Okay. So one thing I do want to say before we continue is that you can see that you're going to need to know your derivatives for all of the basic functions. So I'm going to link from the lectures page, look for a PDF of, the derivatives of common functions. And if you want to get one from someplace, what you might do is you might go to Paul's online math notes. It's a good place to get cheat sheets and things like that. And if you scroll down here, you can see there's one for common derivatives and integrals, and then also some more complicated calculus cheat sheets. So like common derivatives here, you might want the full version or the reduced version. And just to have all these on here. One thing I noticed was they actually like in your homework, you actually need the derivative of the inverse cotangent, which is not so complicated to use, but you have to, you have to have it written down there, right? Um, so you're going to need some of these on this page right here. Um, yeah. Okay. So look for a PDF of something like that on the web page that you should have before you kind of do the homework here. Okay, I think let us oh, I don't like that. So I'm just going to make a comment on derivatives of functions of x, y, and z, or more variables. So comment on partials of functions with more than two variables. They work exactly like you expect. Right? Like formally, um, if you have like for like f of x, y, z, the partial of f with respect to z, which you haven't seen before, well, it's just going to be something like this. It's going to be the limit as h goes to 0, f of x, y, z plus h minus f of x, y, z over h, right? Exactly how you would expect it. And the way you go about this is exactly the same, right? So you would, you still follow the same process where you treat um, all other variables as if they were constant. Okay. So like, let me just write one. We'll do one example and then that should be enough for that. Partial of f with respect to x, partial of f with respect to y, partial of f with respect to z and then we need an f of x, y, z. Let's do like x to the 2, y to the 3, z to the 4, plus x, y, z. Okay, so that's just, an example that's not going to be too hard here. So how would we do this? Well, you take partial of f with respect to x. So we treat everything that's not an x as if it's a constant here. So derivative of x squared with respect to x is simply 2x. Derivative of y to the 3 is going to be 0. Derivative of z to the 4 is going to be 0. And the derivative of x, y, z, so the derivative of x is 1, which would leave you with the yz. Then you got partial of f with respect to y. So derivative of x squared with respect to y is going to be 0 because x squared is a constant for us. Derivative of y to the 3 is going to be 3y squared. Derivative of z to the 4 is going to be 0 because we're treating z's as constants. And the derivative of x, y, z, well, x is a constant, y is a constant, z, the derivative of z, wait, sorry, I just acted like I was doing the derivative with respect to z. Let me resay that. We're treating x like it's a constant, y is a variable, z is a constant. So the derivative of y with respect to y is 1, and then the x and the z are just kind of carried along for the ride. So xz. So one thing you can notice here is like when you take the derivative of xyz, when you take the derivative with respect to x, you end up just with the yz. And when you take the derivative with respect to y, the y is gone and you have an xz. And when you do the derivative with respect to z, well, it's going to be xy. So derivative of x squared, 0. Derivative of y to the 3, 0. The derivative of z to the 4th, well, now we got a z, so it's going to be 4z to the 3 plus here, x is a constant, y is a constant, z is the variable. Derivative of z with respect to z is 1, so you end up with xy. Okay, so there's some partials of functions of 3 variables. You just do it the same way. Okay. Higher order partials. Okay. There's also some kind of like simple applications we're going to talk about after we look at the higher order partials. So let us write it. We need to understand the notation here. Let's see. So for a function of 2 variables, f of x, y, of course, you can compute 2 partial derivatives, right? What are they? They are partial of f with respect to x and partial of f with respect to y. Let me write what we're doing here. Higher order partial derivatives. Okay. So you can calculate 2 partial derivatives, the partial of f with respect to x and the partial of f with respect to y. But for each of those, you can calculate partial derivatives, right? Because they're functions. But not that color, hold on. But now you can compute the partial with respect to x and the partial with respect to y of each of these. To get second order partials, as they would be called. Okay, now the notation might be a little bit confusing here. So let's look at the different kinds of second order partial derivatives, right? So you could do the partial with respect to x of the derivative of f with respect, the partial of f with respect to x, right? So this is partial with respect to x of the partial of f with respect to x. Okay, that's what that is. Let me move this over though. You would write this like this, by the way. So when you're trying to write the notation for it, you have partial symbol, f on top. Partial symbol, f. So we would write that partial symbol squared, basically. That's how they do that, of f. And then on the bottom, you would write, usually you would write like this. Now you might think like, well, how come the delta doesn't have a square on it, right? Because it's partial with respect to x, partial with respect to x. They're treating this as if it's one thing. And so that square is on both. And if that's confusing, well, too bad, because this is just the notation that we use. So sorry about it. Okay, now we could also do the partial with respect to y of the partial of f with respect to x. That would give you partial squared f, and then on the bottom, partial y partial x. So that would be the notation. So what would that be? Well, let me copy this again, duplicate it. So this would be the partial with respect to y of the partial of f with respect to x. Okay. But then there's two more that you could calculate. Because you can also calculate the partial with respect to x of the partial with respect to y. If you do that, it would be partial with respect to x, partial with respect to y on the bottom, and that would be the partial with respect to x of the partial of f with respect to y. Now, I'm going to talk about this a little bit more in a second, but so when you're looking at this right here, like these aren't technically the same, right? Like this is, in this one, you did the partial with respect to x first, and then you did the partial with respect to y, right? This one gets done first, and then this. Here, you did the partial with respect to y first, and then the partial with respect to x first. So like this happens first, this happens second. Here, it's the other way around. So they're technically not the same, but they are related, and there's a theorem and so on that deals with it. Okay. Now, those are only three of them. We could also do the partial with respect to y. Sorry, I said y, so I wrote y. The partial with respect to y of the partial of f with respect to y. That would be d2f dy squared. So that's the partial with respect to x of the partial of f. I said x, but partial with respect to y of the partial of f with respect to y. Okay. Now, as far as notation goes, there's a little bit more notation. So, more notation for these. If you have partial d2f dx squared, another way to write that would be fxx, right? So you're just saying take x derivative and x derivative. Now, if you have partial with respect to y, d2f of dx, actually, what do we want? We want dy dx, I think, like that. And what's a little bit tricky is you have to remember what order you do things in here. So, like, hold on here. Did they even explain it? I'm looking in your book. Hold on a second. Yeah, I think they don't. That's really terrible of them to not do that. Um, but yeah. So one thing you want to be aware of is like the notation for this would be this. And specifically, one thing you want to notice is that, right, in this notation, the notation on the left, you did the partial with respect to x first, and then you did the partial with respect to y. And in this notation, you do the partial with respect to x first and then y. And what you're noticing is that the xy, it's in the order xy here, but it's in the order yx here. because in this notation, the notation here comes from this idea up here that first you computed the partial of f with respect to x, and then you applied this partial with respect to y on the outside. And so the partial with respect to y is on the left. And so it's on the left. So this is first, this is second. But in this notation, this is first, this is second. This is first, this is second. So it's a little bit, confusing to see that, but that's the way the notation goes. And then you got, the other mixed partial. I didn't say those words before right now, but right. So this one's first, and finally d2f dy squared fyy. Okay, so just notice the order. Right, so in this one, you do, right, you start with f, take partial with respect to x, and then partial with respect to y. Right, and then this one is reversed, where you start with f, take partial with respect to y, and then partial with respect to x. Okay, so notationally, it can be a little bit confusing there. Another comment here is note fxy and fyx are called the mixed partials commonly. Right, and it's obvious why they're called mixed, right? Because it's a partial with respect to x and then a partial with respect to y. Okay, so that idea can be extended. Yeah, I mean, that can be extended into 3 dimensions or 3 variables and so on. Okay, so a comment on the relationship between the mixed partials. So there's a theorem, important theorem, you should know it. So this is theorem equality of the mixed partials. I guess it has a name. They call it, not 100% sure how to pronounce this. I'm going to write it and then I'll say it. Try to say it. I don't know how to pronounce the name. It looks French. So if it's French, I would say it's probably Clairaut, right? That looks AOU is going to be O. So Clairaut's theorem, maybe. And anyway, what's not important is the name. The point, what is important is what the theorem is. So it is if f of xy is continuous on an open disk D containing point AB. So you just need a continuous function. That's all we're really saying here. If f of xy is continuous in some region, then hold on. No, that's actually not quite right. Okay, hold on. So if f of x is defined on an open disk D containing the point AB, and f of xy and fyx, I said that wrong, fxy and fyx are continuous, on D, then fxy equals fyx, right? So basically what that's saying is if the partial derivatives are continuous, then if the mixed partials are continuous, then they're equal to each other, right? That's what that's saying. Okay, so yeah. Also notice that this theorem is written in a really weird way in your book, right? Defined on an open disk D containing the point AB. What's AB? They never mentioned it after that. Presumably what they mean is that f of xy evaluated at AB is equal to f of yx evaluated at AB. But they didn't say that. Okay, so if the mixed partials are continuous, then they should be equal to each other. That's the thing. Now, the reason you would care about that is sometimes you could save yourself a lot of work. So like, for example, let f of xy equal, like, let's say x squared plus sine x to the 3 over x plus 1 plus x squared plus y squared. Okay, now let's say I say find, compute fxy and fyx. Okay, and I'm using the alternate notation for those partials now. So let's do f of xy first. All right, so how are we going to do it? So f is x squared plus sine x cubed over x plus 1 plus x squared plus y squared. So if I'm going to do the partial with respect to x, when I do this derivative here, I'm going to have to do the quotient rule, right? I specifically wrote this so I couldn't avoid it here. I'm going to need the quotient rule. So I have to go the bottom function times the derivative of the top, which is 2x plus 3, oops, what happened? Plus 3x squared cosine x to the 3. Hopefully, am I right there? Hold on. Yeah, cosine x 3x squared. Okay. Minus the top times the derivative of the bottom, which is 1, over the bottom squared, and then plus the derivative of x squared with respect to x is 2x, and the derivative of y squared with respect to x is 0. So this is your first derivative, fx. Now, if you want fxy, you need to take the derivative with respect to y of this. So let's take the derivative with respect to y of this function. Well, there's no y's here, so that derivative is 0. And there's no y's here, so that derivative is 0. Okay? Now, it's a little bit tedious to do here because we had to do that quotient rule, right? Now, if we do the derivatives the other way around, if we do fyx, again, we're starting from the same f. So let me just duplicate that, break it down. If we do partial with respect to y first, this time you don't have to do the quotient rule, right? Because you're going to take the derivative of this thing first with respect to y. There are no y's, so that derivative is just 0. Here, the derivative of x squared with respect to y is 0, and the derivative of y squared with respect to y is 2y. And then when you want to do fyx, that's the partial with respect to x of 2y, which there's no x, so that partial is 0. Point is, you get zero both times, right? So both fxy equals zero and fyx equals zero, which the theorem said, right? Because these zero is a continuous function. Okay. So, which of these was shorter though, right? So if you had to calculate fyx or fxy, you should do it this way instead of this way because this way is more complicated, right? So the point is, if you're asked for fyx or fxy, you can compute fxy or fyx, whichever one's easier, whichever one you think is easier. As long as the partials are derivative. So as long as the result is going to be continuous. Okay. So, and that actually gets used for stuff. If you take more advanced math classes, you'll be doing things like checking, like using the result that the mixed partials are supposed to be equal in order to do, more complicated things later on. Okay. That's most of the homework here. What I want to do is there's one kind of problem that I haven't gone over yet, and I wanted to talk about it. Specifically, um, it's going to be the interpretation of the partial derivatives in terms of like slopes. Okay, so I guess I'll write it here. Uh, Partials and slopes. Okay, so it's a little bit weird. This is actually not really a 4.3 kind of thing. It's more of a 4.4 kind of thing, but I guess it's there. So in calculus 1, the derivative is the slope, right? Like dy dx evaluated at a point. Oops, not AB, just A. Is the slope of, y equals f of x. Actually, let me just rearrange this. Okay, so two notations for the same thing here. Like dy dx evaluated at x equals a, or f prime of a is the slope of the function y equals f of x. So y and f are the same thing at the point x equals a, right? So you know what that looks like, of course. Right, you've got your function like this. That's y equals f of x. You've got some point A. You come up here, and the slope of this tangent line right here is going to have slope f prime of a. So that's how it works in calculus 1. You should be, familiar with that. So in calc 3, the partial derivatives are slopes, but they're slopes in particular directions. So on a surface, um, you can have different slopes in different directions. Okay, so what does that look like? Let me see if I can show you. So I'm gonna try to draw a surface. Okay, so I just need a surface here. So I'm gonna go like, there's my surface, right? So think of it as like, right? So like you've got a surface there, um, just floating up in space. Okay. Now, if you take a particular point on this surface here, right? Like let's say right here, um, and that point could be like, let's say AB, then the slope in the y direction and the slope in the x direction aren't necessarily the same. So you've got one slope in, let me erase this a little bit so I can write on it. Okay, good enough. Let me put my point back. Actually, I'm going to move that point to a different location. I'm going to put it up here. Okay, that's going to be AB. Okay, so if this is your, sorry, trying to write, if this is your X and this is your Y axis, then from this point here, the X direction is like, let me pick a color, red. Okay, so like the X direction is this direction, right? And the Y direction would be like this direction. Okay, so I'll just write X and I'm gonna write Y. Okay, so from a particular point along the surface, so from a point AB, um, you know, there is one slope in the positive X direction and another in the positive Y direction. Right. So, like, for example, depending on what your surface looks like this slope might be like -1/2, but this slope might be -2, right? It might be a steeper drop off in this direction as opposed to this direction. There's no guarantee that they're the same, right? It just depends on what kind of surface you have. And so, how do you calculate those slopes? Well, that is another application of the partial derivative. So we could just say like this, for example, specifically for f of xy, the slope of f of xy in the x direction at the point AB is given by, well, what do you think it is? Probably makes sense, right? It's going to be the partial of f with respect to x, and then you're going to evaluate that at a comma b. And you call that like m, right? That's a slope. And if you do this again, you can say the slope in the y direction at AB is given by, I'll call it m again. This time it's the partial of f with respect to y evaluated at AB. And again, they could be positive or negative. One can be positive, one could be negative. There's no real, like, there's no restrictions on it that way. So, yeah. we're going to use these more in the next section to get a tangent plane, right? Just like you can get a tangent line, you can get a tangent plane to a surface. So in section 4.4, we will use this to compute tangent planes to surfaces. Which is not, I mean, it's not as complicated as it sounds there. Like if you got your surface, again, I'm going to try to draw kind of the same kind of surface that I drew before. Just kind of some surface, right? What you can do is you can do that way too high here. You can take a point on the surface just anywhere, like right here, for example. And right there, using the slopes in each direction, you can find like a tangent plane to the surface. It's like a tangent line, but it's a flat plane, right? It's like putting a sheet of paper on an orange. I don't know why, but I don't know why that makes more sense. But right, orange. Actually, I want to draw it flatter. Piece of paper, right? Tangent plane. So we're going to use the same idea to calculate tangent planes in the next section. For now, we don't have tangent planes. They're just going to specifically ask you to find the slope in the y direction. So something like that. So like, for example, let's just do the example. This is straight out of the book. They say find the slope in the y direction of f of xy equals -6 plus 9, -7 plus x quantity squared. Oh, that's just ridiculous. Plus 9, -6 plus y squared at the point -1 to 714. Okay, now the first thing here is that to notice that you're not going to need that z value 714 for anything. Okay, just kind of make a note of that. Okay, the point is the AB, right? That's the x and the y coordinate. So it's just the -1, 2. Okay, you don't need that 714 for anything. Okay, with that said, we're going to need the y derivative. So we're going to start with this function here. We're going to start with this function and we need the derivative. So we should compute the y derivative, partial of f with respect to y, because we're doing the slope in the y direction. So partial of f with respect to y is going to be, well, let's do it. So the derivative of -6 is 0, of course. The derivative of 9, -7 plus x squared, there's no y's there. So the derivative with respect to y is again 0. And then here we've got this derivative. We can use the chain rule here rather than multiply this out. So to take this derivative with the chain rule, you would take the 2 down in front, combine it with that 9 to get 18. You have -6 plus y, subtract 1 from the power. Then you multiply by the derivative of what's inside. So the derivative of -6 plus y with respect to y is 1. So our partial of f with respect to y is simply 18 times, and I'm going to switch the order here to make it look nicer, y minus 6. Okay, so that's your partial with respect to y. Now what we haven't done is evaluate it at the point. So the slope in y direction at -1 comma 2 is going to be this partial derivative df dy. I keep saying df dy, but you're going to plug the -1 comma 2 into this function. So it's it's 18 times y, which is 2 minus 6. So it's 18 times minus 4, which is -72. There's your slope. Okay. So when they ask you for the slope in a particular direction, they're really just saying find the derivative, and then plug in a point. Okay, I think that's all the different kinds of questions, really. Well, I mean, there's one slightly more complicated, like with like a small word problem, but I'll let you guys try it because it does boil down just to finding a derivative and plugging in a point again. Okay, so yeah, I think that's it for now. And talk to you guys later.